This is the first PowerPoint video for Chapter 7, which is on solutions. The topics that we're going to be looking at this morning are solutes and solvents, electrolytes, equivalence, and solubility. Now, solutions are homogeneous mixtures, which means if you make up your mixture, no matter where you would test your mixture, here you can see we have salt water. No matter where you would test your salt water, you get the same ratio of salt to water. And in a solution, we have solutes and solvents. Now, the solute is the substance present in the smaller amount, and the solvent is a substance present in the greater amount. If water is involved, then water is always called a solvent. Other than that, go by the amounts. Now, solutes are evenly spread throughout the solution, and in our example here we have some copper 2 sulfate, which we've used a couple of times this semester, and we have water. And so this first representation is here. We have the solute sitting at the bottom and water is put on top of it, and they just let it sit there. And over time, the copper 2 sulfate particles will be suspended throughout the liquid, as you can see here. If you try to separate this solution using filter paper, all of it will just pass right through the filter paper, so you won't be able to separate the solute that way. But you can separate it by evaporating the water. Now, the solute particles are so small they're not visible, and they don't reflect light at all, so you won't be able to see them. And they may give a color to the solution like this one does here, or they may not. So a solution can have a color, but it has to be clear to really be a solution. This is a chart from the textbook that shows you the different phases involved in solutions. We think of solutions normally being a solid and a liquid, but as you can see, it can be any phase in any phase. So we start off by looking at the first one. We have a gas and a gas. The example is air, and in air, nitrogen is a solvent because there's more nitrogen than anything else in the air, and oxygen is a solute. Now, liquid solutions, we can have a gas and a liquid like soda water or household ammonia, and again, the water is going to be the solvent. A liquid in a liquid would be like vinegar. Acetic acid is the acid in vinegar, and that's a liquid by itself, and so vinegar is normally a 5% solution, which means only 5 grams of acetic acid and 95 grams of water. And then we have a solid and a liquid. We could have that sodium chloride would be our example, or we could have a tincture of iodine. A tincture actually means that the solvent is ethyl alcohol. And so again, we don't have to have water, but if we, go back on that. And let's finish up, bouncing all over the place here, with a solid solution. Now, you don't think about solids giving a solution because definitely they're not clear. But because the solute is spread throughout the other solid, it's called a solution. So a dental amalgam, if you have a dental filling, the old type fillings, then you have a mixture of silver spread throughout mercury. Now you might say, well, see, there's more silver than there is mercury. That's why the silver is the solvent. Now you have a solid in a solid, brass, which is a compound or mixture really of zinc and copper, and steel, which is a mixture of carbon and iron. So you can have all different phases mixed with other phases. Now, water is the most common solvent. In fact, it's called the universal solvent because it can dissolve almost everything to some extent. Even when we say it doesn't dissolve things, it probably does to a very, very tiny, tiny bit. Now, water is a polar molecule, and we've seen this before when we covered bonding. Water molecules can form hydrogen bonds with each other, and here we can see the hydrogen bonds, which are represented by the dotted lines. And so we have 3 water molecules shown here. And the oxygen end of the water molecule is partially negative. That's what that little symbol means. And the hydrogens are partially positive. So the oxygen end of one water molecule is attracted to the hydrogen end of another. And they bond together weakly. Now these hydrogen bonds are not as strong as the bonds within water molecules. They're about only 1/10 as strong as those. But they still are strong enough so that when water forms ice, and you get hydrogen bonds in 3 dimensions forming, that the water can burst right through metal pipes. So to say they're weak is really not correct. Now what happens when we put sodium chloride in water? Now when we do that, because sodium chloride is made up of sodium and chloride ions, charged particles, the water molecules are attracted to them. Now the water will bond to those ions and be able to pull them right out of the solution, right out of the crystal, I mean. And when they do that, the water molecules surround them, and that's what is said to be hydrating them. So down here we have the hydrated ions. So we have the sodium ions and the chloride ions surrounded by water molecules. You notice that for the sodium, because it's positively charged, we have the negative ends of the water molecules pointed in. And it's the opposite for the chloride ions. Chloride being negative, we have the hydrogens all pointed in like that. Now, so they weakly bond to that. And this is why if you have a lot of sodium in your system, it'll retain water because the water is bonded to it. And here's a little equation showing the sodium chloride breaking up in water. You notice I'm not saying plus water here as if it was a chemical reaction. This is a physical reaction. And we can get the sodium chloride back by just evaporating the water. Now here's something that you want to really understand because it's something we use all the time, and it's the phrase like dissolves like. And to show that, we're going to say that we have basically two types of solvents. Water, which is polar, and other compounds which are nonpolar. This one would be called dichloromethane, but there are many nonpolar solvents like gasoline is nonpolar, kerosene. All your oils are nonpolar because they don't mix with water. Now for this example here, you notice we put these two liquids together into 3 test tubes and they separate immediately. The water is on top because it's less dense than the dichloromethane. Now I'm going to add some iodine to the 2 of these test tubes, and I'm going to add to this test tube, and I'm going to add some nickel 2 nitrate to this test tube. Let's see what happens. When we do that, the iodine dissolves in the nonpolar dichloromethane, and that's because iodine itself is nonpolar. Whereas the nickel 2 nitrate dissolves in the water, but not in the dichloromethane. So let's see what's going on here. Well, water molecules, because they have little charges on them, are attracted to anything else with charges. So they're attracted to the nickel 2 nitrate because we have nickel and nitrate ions. That's why they dissolve in here. But because there are no charges on the dichloromethane, they're not attracted to the nickel 2 nitrate, so nothing's happening here. And as far as the iodine goes, water is not attracted to the iodine either because of the water molecules, because of their charges, are more attracted to each other than they would be to the iodine. Now you might say, well, I don't know, when I put iodine in water, I see a tiny little yellow color. Well, again, there is a little solubility, but we wouldn't really call it soluble. So let's see how much you know so far. So here's a little quiz for you. So you want to stop and answer these questions, and then pause the video, and then you can start again. All right, so answer the questions, and then I'm going to give you the answers. Okay, here are the answers. So which ones are the solutes? Well, sugar would be the solute for 2 reasons. Number 1, there's less of it than the water. And number 2, water is always considered to be the solvent when it's there. How about letter B? Now, neither one has water. So it would be the methyl alcohol because there's less of it than the ethyl. And for letter C, it would be the sodium chloride because, again, it's with water and there's less of it. And for D, it's going to be the oxygen because there's less of that than the nitrogen. Okay, pretty easy. How about this one? So solid lithium chloride is added to water. It dissolves in water because, now what do you think? Lithium ions, are they attracted to the oxygen or the hydrogen ends of the water? And the chloride, which ions are they attracted to? So I'm going to pause for a second and write down your answers, and then we'll check them out. Okay, here are the answers. For the first one, it's going to be the oxygen end because lithium is positive and the oxygen end is partially negative. And in B, it's going to be the hydrogen end, just as we saw with the sodium chloride. Now, here's another question. Which of the following solutes will dissolve in water and why? So, which ones would be water soluble? So we're going to pause this and write down your answers and then come back and check them. Okay, here are the answers. It would be sodium sulfate, Na2SO4, because that's made up of ions and they have particles with charges, and water be attracted to them. And for letter D is HCl, which is polar. So remember, like dissolves like. So water can dissolve water cannot dissolve nonpolar. Water can dissolve polar things because it's polar, can also dissolve ionic things because they have charges. So you want to remember that rule. Okay, let's continue on. So now we're going to talk about the solutes themselves. We have three basic types of electrolytes. We can have strong, weak, or non-electrolytes, and we can put solutes into those categories. So a strong electrolyte is one that produces a lot of ions, and because of that, the water solution will conduct a current. So we have a light bulb set up with these two electrodes from the light bulb sitting in here. Now this follow the plug. This plug would be plugged to an outlet. So I don't want you to think that the solution is making electricity. It's not. It's simply allowing the electrons to go from one electrode to the other. And you can see why that happens. The sodium ions are attracted to the electrode with the electrons. So it's going to come over here and take in electrons, and the chloride ions are attracted to the positive pole, and they'll release the electrons here, and that kind of conducts the charge. Now, will this go on forever? No, because you're going to run out of ions moving like this eventually, so the cell will die off eventually. And here's an equation showing the sodium chloride being a strong electrolyte. So we have the single arrow making a lot of ions. Now, for a weak electrolyte, here the example is using HF, which is hydrofluoric acid. And for the HF, we have it weakly reacting with water. In water, most of it stays as HF, so you don't get many ions produced, and then the charge is conducted weakly. And in our equation, we have a double arrow showing we have a reversible reaction. And a non-electrolyte would be something like sugar. Now, sugar dissolves in water very well, but because it doesn't break up into any ions, it can't conduct electricity. So we can still write an equation for it, but you notice there are no ions on the right-hand side of the arrow, just as AQ. So can you recognize three different types of electrolytes by the equations? For a strong electrolyte, there'll be a single arrow with ions as products. For a weak electrolyte, a double arrow with ions as products. And for a non-electrolyte, you'll have a single arrow with no ions produced. Now let's take a closer look at some of those so you can really understand what it means to be strong or weak. Let's say I took my sodium chloride and I weighed out a mole of it, and I'm going to add it to water. So in the beginning, before I've added it to water, I don't have any ions, I just have the solid. At the end, all of this would have dissolved, and I will have wound up with a mole of sodium and a mole of chloride ions. That's what it means to be a strong electrolyte. All of it will dissolve. Let's take a look at this one, barium chloride, which breaks up also very strongly. Now, if I have 1 mole of barium chloride in the beginning, at the end, look at the ratio now. You notice that I get 2 moles of chloride? I can get that from my equation. So barium chloride, if you're comparing barium chloride to sodium chloride, mole to mole, barium chloride produces more moles of ions than sodium chloride. This would also be a stronger electrolyte because it produces more ions. And here's our HF again. Now, double arrow says it's a weak electrolyte, and let's see what that really means. If I started with a mole of it, at the end, almost all of that is still present, and only 1/100th of it really reacted. So the number of moles of ions is tiny. That's a weak electrolyte. Now, equivalence is a type of concentration unit that's used in hospitals, and that's why we're mentioning it here. An equivalent is the amount of an electrolyte, or an ion, that provides 1 mole of electric charge. So think of it provides 1 mole of either positive or 1 mole of negative charge. So 1 mole of sodium ions would be equal to 1 mole to 1 equivalent. 1 mole of chloride ions is 1 equivalent. 1 mole of calcium ions is 2 equivalents, and that's because of the charge. 1 mole of iron 3 ions is 3 equivalents. So to get the number of equivalents, we take the number of moles of the ions that we have and multiply it by the charge. And we can do this either to the positive or the negative ions in the solution, and it wouldn't matter. So you notice if we had sodium chloride, it would be 1 mole of sodium chloride is going to give us 1 equivalent, because it's going to give us 1 mole of sodium and 1 mole of chloride ions. Now in the body fluids, because the concentration of electrolytes is so small, they measure the concentration in milliequivalents, which really means thousandths of an equivalent per liter. So a ringer solution is a common solution to give to people if they have, lost a lot of blood volume. So that solution has to have the ions in it that match what ions we would have in our bloodstream all the time. You just can't give people water if they've lost blood. You actually would wind up killing them. So let's see. The sodium concentration is 147 milliequivalents, and the chloride a little bit higher. That means something else must be providing chloride besides sodium chloride. Potassium ions, 4 milliequivalents. Calcium ions are 4 milliequivalents as well. So you notice if we add up all the milliequivalents for these ions, what's it equaling? It's equal to negative. So the total concentration of the positive and the negative have to be equal. And this is right out of the book, table 7.5. So in blood plasma, cations, look at the cations here, and they're showing a total of 150. And the anions, which mean negative ions, we get a total of 150 again. You can see the person putting in the solution now, lactated Ringer solution. So let's see how well you can do on this now. Here's a little quiz. You have 3 questions about equivalents and milliequivalents and ions. So pause the video and answer these questions, and then come back and see the answers. Okay, here are the answers. For number 1, it's going to be 3 equivalents. All you have to do is multiply the positive 3 charge by the 1 mole. Letter B is going to be 5.0 equivalents, because now it's going to be 2.5 moles. There's my arrow. 2.5 times 2. That gives me 5. And for the last one, it's going to be 34 milliequivalents, because if it's just sodium chloride in the IV bottle, if the sodium is this, then the chloride must be the same, because again, this total charge has to add up to 0. All right, the next topic here is solubility. And solubility means the maximum amount of solute that dissolves in a specific amount of solvent. And we usually express that concentration per 100 grams of solvent. So we'll talk about grams of solute per 100 grams. Because that's like anything out of 100 really means like percent, so we're used to that. So that's going to give us a little ratio of grams of solute per 100 grams of water. And there are graphs that'll show us this information. So an unsaturated solution contains less than you can actually dissolve at that particular temperature. So here we have somebody adding some solute to water, and all of the solute dissolves, you notice. That means you can still dissolve some solute. You can't tell if it all dissolves. That you can't say, well, I've dissolved all that I can. The only way you can tell is if you can still dissolve some more. A saturated solution, on the other hand, contains the max amount that you can dissolve. How would you recognize that? Because you have to have some undissolved solute sitting on the bottom of the beaker, even after stirring it and shaking it. And so it just doesn't sit there and do nothing. It actually dissolves, but it recrystallizes at the same rate. What we see is no change at all. Now let's take that information and put it in a graph. So here we have a graph of solubilities of a whole bunch of different substances. So at the bottom, you notice we have temperature rising as we go to the right. And on the left, we have the amount of solute increasing. And that's going to be grams of solute per 100 grams of water. So we have all different solutes here. Most of them show that as the temperature goes up, the solubility goes up. And there are a couple of odd ones, like here's ammonia. And here we have, in purple, we have sodium sulfate. So that says sodium sulfate is actually more soluble in colder water. And ammonia is much more soluble in cold water. So solubility depends on temperature. For most solids, it increases as the temperature increases. We saw the sodium sulfate being an exception. And for gases, it decreases when the temperature goes up. So we have the graph for the ammonia showing us that. So this means that if you have an ammonia cleaning solution at home, and it tells you to add some of that to water, should you use hot water or cold water? Well, hot water is better for cleaning, but if you put the ammonia solution in hot water, you'll drive most of the ammonia out, and you'll be overcome by all the fumes. What about cold water? Well, cold water isn't as good for cleaning, so you want to kind of compromise, probably like lukewarm water. Let's see if we can answer a couple of questions using the graph now. So, is a solution made of 80 grams of KNO3 and 100 milliliters of water at 40 degrees saturated or unsaturated? So, what we want to do, I'm going to get my pen out here. What we want to do is locate the line for KNO3. So here's KNO3 up here. And it says 100 milliliters of water. 100 milliliters is the same as 100 grams. Now I want to find where 40 degrees would be. So here's my 40 degrees. So what I do is I follow that line up until I hit where KNO3. Here we go. See that? I'll put that point there. That's where the KNO3 crosses 40 degrees. So now let's see where the 80 grams is. Well, 80 grams is right here. So 80 grams is actually at that intersection. So what does that tell us about the solution? The solution is saturated. So if you use this graph here, if the conditions put you right on a point for that substance in question, that means it's saturated. Now that would mean if somebody added 60 grams instead, which would be down here, see that would be where the 60, that means the solution would be unsaturated and could still dissolve 10 more grams. Now let's check this one out. There's a solution made of 80 grams of glucose in 100 milliliters of water, 40 degrees saturated or unsaturated. So let's find glucose. Now here's glucose up here. Here we go 40 degrees, and it would be right here. There's that dot. Okay. And if we look left, it's right about there. Looks like about 130 is how much you could dissolve altogether, and they only have 80. They only have 80 grams dissolved. So that means the solution would be unsaturated. And that's how you can read the graph. You'll see questions in the textbook where they'll give you the graph and ask you to answer questions just like this. So how many more grams of glucose could dissolve? Well, let's see. We only put in 80, and we said maybe about 130. So I would say, okay, 130 minus 80, we could dissolve 50 more grams. All right, now let's see if you can answer these two questions. Label each of the following solutions as saturated or unsaturated. Salt disappears when put into water. Sugar added to a cup of water does not disappear but sits at the bottom of the cup. I think that meant that they've also stirred this around. All right, so pause the video and then come back and check your answers. All right, here are the answers. First one would be unsaturated because you can still dissolve some more salt. That's what we have to assume. And for B, it would be saturated because we have some sitting at the bottom, and that's the key thing there. All right, let's see if we can answer these three questions. At 40 degrees, the solubility of KBr is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated, and then explain. Okay. So 60 grams and 100 grams of water at 40 degrees. 200 grams of KBr and 200. Notice to change the amount of water. If the amount of water changes, then the amount of KBr would change proportionately. You could still use a graph on this if you needed to, or use this data. And for the last one, notice they cut the water in half again. Right, and up here, though, they're telling you it's 80 grams per 100 grams of water. So you have to use that information down here. The temperature doesn't matter now because that's going to be the same in each one. So pause the video, answer your questions, and come on back and check the answers. Okay, here are the answers. For A, it would be unsaturated because you've only dissolved 60 grams and 100 grams of water, and it's telling us you can dissolve up to 80. That means you could probably still dissolve 20 grams more. So that's an easy one. How about saturated for B? Why is this one saturated? Well, you know, it says 200 grams of water. 200 grams of KBr and 200 grams of water. That would be the same as 100 grams of KBr and 100 grams of water. So what we're really doing is comparing these numbers. And since the maximum is 80 grams per 100, and they have 100 dissolved, that means it's saturated. And that doesn't mean that they dissolved 100. That means that they have some excess sitting on the bottom. Oops, and go back to the last one here. Why is this one unsaturated? Again, we want to change this for 100 grams of water. So 50 grams, we can double that, multiply by 2 to give us 100 grams of water. That means multiply this by 2. So 25 grams of KBr in 50 grams of water is the same as 50 grams of KBr in 100 grams of water. So it's the 50. It's the 50 then that we're checking out. So 50 is less than 80, so therefore unsaturated. I know those questions can be a little tricky, so you might want to go through this a couple times. Okay, we're coming up near the end now. So now we're going to be talking about Henry's Law, which talks about dissolving a gas in a liquid. And it's really a gas that is not normally very soluble in water. So our example is going to be a can of Coke, and a carbonated beverage contains CO2 under pressure. So Henry's law states that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. What does that mean? That means in order to make CO2 dissolve in water, which essentially is what a carbonated beverage is, I have to use high pressure on that CO2. So normal air pressure for CO2 is very small. If I just use that, hardly any CO2 will dissolve. So I have to put CO2 under pressure to force it into it. So that's what Henry's law is all about. That's why at high pressures more gas molecules dissolve in the liquid. Now opening the can, you release the pressure and the gas comes out right away. Now if you see the difference here it is down here before we've opened it up, and see you have a lot of gas, a lot of CO2 molecules above the liquid, and a lot of CO2 in here. And what happens then? The gas takes off, and so the solution is becoming flat as this happens. That's why you have to drink that can up, not rather quickly, but you don't want to leave it open like that for a day because you won't have enough CO2 left in it. Let's see how you can do with these questions now. Why could a bottle of carbonated drink possibly burst or explode when it's left out in the hot sun? Why do fish die in water that is too warm? So pause the video for a minute, answer your questions, and come on back and check them out. Okay, here are the answers. The pressure in a bottle increases as the gas leaves the solution when it becomes less soluble at higher temperatures. So as pressure increases, the bottle could burst. So what this means is that can heats up in the sun and heats up. You drive the CO2 out of the solution, and it kind of builds up a lot of pressure, more than normal, above the liquid in the can. And that means that it could explode possibly. It also means that if you start off with a very, very cold can of a carbonated beverage, you'll have less CO2 above the bottle and more dissolved. So when you first open up a can of a cold, let's say if the can is very cold, you get less carbonation, less fizzing than you would get if you open up a can that's at room temperature. The reason we refrigerate carbonated beverages is to try to keep the CO2 dissolved in it so the carbonation lasts longer. If you'd open up a bottle of a cold beverage and a warm beverage at the same time, they're both carbonated now. The one that's warm would lose its gas much faster than the one that's cold. And then for the second question, because O2 gas is less soluble in warm water, the fish are going to actually suffocate. And so you have to keep adding oxygen to the water. So you might have a fish tank at home, and if you do, you have a little aquarium. You have to keep bubbling air through that water to try to get some of that oxygen to dissolve in it. Not much dissolves in it, but enough to keep the fish alive. But if you just leave the fish in a bowl of water, they're going to die. As the water will warm up, they just lose that oxygen and they're going to suffocate. And that's the end of the slideshow.